record this meeting actually. Okay, so our differential form, if I give you something like y equals 3x squared plus 5x minus 4, you're going to get dy over dx, meaning take the derivative of y, so take the derivative of that function with respect to x, and you're just going to have, since everything is in terms of x, there's no real implicit differentiation here, everything is explicit, we're going to get 6x plus 5. Everyone is pretty comfortable with that. What we haven't really talked about is our differential form, which is exactly this same information. All we did was isolate the dy. So to isolate the dy, you would multiply the dx over. And so our differential form down here in black is going to be dy equals 6x plus 5 parentheses dx, because that dx would apply to everything. That is the exact same information as the one above it. It's just a different way to write a derivative. Okay, so dy equals 6x plus 5 dx is the same information as dy over dx equals 6x plus 5. That's going to come in handy for several things we do, but especially U-substitution. Okay, any questions on that so far? Everyone's decent on this, I think. All right, let's jump into the fun stuff. Please go ahead and write this down. You can write down what I wrote at the top if that's helpful. U-substitution is like product, quotient, chain for integrals or antiderivatives. That's what we're going to use U-substitution for. So if I gave you this function here, and I asked you to take a derivative of that, which we're not asking, but if I gave you that function there and I asked you to take a derivative, hopefully you can see, well, in that function, I would have product rule and I would have chain rule. Since that's true, that means I'm going to need to use U-substitution in order to take the antiderivative. Okay, if I need product, quotient, or chain to take the derivative of a function, if that same function appears in an integral, I'm going to need U-substitution. Okay, now the way U-substitution works is a little confusing, so hopefully you watch those videos and we're going to go through some examples that will help. Okay, I think Nancy is her name. She talked about inside and outside functions. We've kind of talked about that before. That's one way to think about this, our inside functions and our outside functions. Like I have something raised to the 5th. So I have a function inside of a function. A lot of times, not every time, but a lot of times if you have a function inside of another function, there's a good chance that that's your u. But the thing that has to be true for whatever we choose for our u is that its derivative must be available. And its derivative must be available even if we're missing a constant in that derivative. So what we're going to choose for our u, we'll do this example together first, is x squared plus 1. You always want to choose, if there's a constant, you want to include that in your u. So we don't want to just choose x squared. We want to get rid of as much stuff as possible when we're doing U-substitution. So instead of just choosing x squared, we're going to choose x squared plus 1. And now what we're going to do is we're going to take the derivative of u with respect to x. We're going to take the derivative of u with respect to x, but we're going to write it in our differential form. Meaning instead of writing du over dx, I'm going to write du equals, and my dx is going to end up on this right side. Okay, just like we did on the previous example. So now I'm just taking the derivative of x squared plus 1. For the derivative of x squared plus 1, I get 2x. So our differential form is du equals 2x dx. Now we can substitute anything that was an x or an x squared or an x dx or anything like that. We can substitute that out and replace it with what it's equal to. Right? So wherever I had x squared plus 1 in this integral, right, which was right here, this was x squared plus 1, that is now equal to just u. So we're going to replace the x squared plus 1 with a u. That's going to go in there for x squared plus 1. We're substituting in our u. That was still raised to the 5th power, so we still have a 5 up there. Now, when we took the derivative of u, we got 2x dx, which you'll notice we also have right here, 2x dx. That gets replaced with what that's equal to, which is a du. So we're going to have a du right here. Your antiderivatives or your integrals should always start with this sign and end with a d something. You should never have the du like in the middle somewhere. It should always be at the end, like a period on a sentence. Okay, now all we're doing is taking the integral of this function, or taking the antiderivative of this. So the antiderivative of this, now the only rule we need is power rule. So now we can take the antiderivative as is. When we take the antiderivative, you guys remember we're adding 1. Oops, sorry. So we're adding 1, we get u to the 6th, and then we divide by that number over 6, and then plus c. So remember, we always could have lost a constant when we took our derivative. So we're always going to have a plus c. Now the final step I need to do, since the original question had x's in it, I need to substitute back in what u was equal to. So u was equal to x squared plus 1. We just substituted it momentarily so that we could take the antiderivative. Now we're going to substitute that back in, meaning our final answer here is going to be, instead of u to the 6th, it's going to be x squared plus 1 to the 6th all over 6, and then plus c. We talked about this in class on Friday, but a way to check this answer is to take the derivative of this function. If I were to take the derivative of this, yes, I would need chain rule. I would multiply, or I'd bring down that 6. I'd have 6 over 6, x squared plus 1 to the 5th power, times the derivative of the inside function, so it's times 2x, and then the derivative of the c would go away. So you end up, 6 over 6 is just 1, you end up getting what we had to start. You can always check your answers by taking the derivative of them. Any questions on this first problem? Please ask questions if you have them. I know most of you won't be here, or several of you will not be here for the whole week. So definitely ask questions if you have them. Yes, go ahead.
Oh, go ahead.
Okay, yeah, I was just wondering what happened to the du. Did it just like, because I know like from yesterday's video, they said it just like vanished, but I didn't really understand why.
Yeah, so if you guys remember last week when we were doing these antiderivatives and we set them up, like let's say we just had an antiderivative of x squared dx. In the context of this, what does this dx actually mean? Do you guys know what that dx actually means?
With respect to x?
It just means with respect to x, and that's all it means here also. It just means with respect to x. And so the du just means with respect to u. So again, this thing, what this actually says in the way that we've written it is take the antiderivative, that's what that first symbol means, of this with respect to u. So it goes away because it's just telling us what we're taking the antiderivative with respect to. Just like if I were to take a derivative, if I were to say d over dx of x cubed or something like that, this dx also goes away because it's just telling us what we're taking it with respect to. Okay, now I know that's confusing because part of that du is the derivative of u, and then it kind of transformed into with respect to u based on its location in the problem. And that's okay. That is what's supposed to happen there. Okay, that's a tricky concept. Does that help a little bit with what happens to that du? That du always is going to go away because it's just telling us what variable to take it with respect to. We can't do an integral if it was like u cubed dx. We have no way to take that integral because we need this letter, that variable, to match the variables inside of the problem. We can't have a combination of variables in there. At least in Calc 1, we can't. Good? Okay. All right, let's go on. Let's do another one. So go ahead and write this down. We have 5 cosine of 5x dx. Okay, so again, you'll notice in this one, we would need trig. Trig alone doesn't require us to do U-sub. We did lots of trig last week. But inside of that cosine function, we have another function, which is where chain rule would come in. Like if I asked you to take the derivative of this function, we would need not only trig, but we would need chain rule. And so that's why we need to use U substitution here. We want to pick something whose derivative is available to us. Does anyone have a guess at what our U is going to be in this case?
5x.
5x. And another way to think about it, just like Nancy said on that video last night, was it's our inside function. If I have cosine of something, a lot of times, not every time, but a lot of times, whatever is inside is going to be our U. Okay, now we take the derivative, so we get du. We're going to write this in our differential form, meaning our dx is going to go on the other side. So we get du equals something dx, and now we just take the derivative of the 5. We get a 5 dx. Okay, now we're going to rewrite our integral. Now, some guys get confused here because they see the 5x, like they know, okay, I'm going to replace that part with a u. But I don't have 5 right next to dx in this case, and that's okay. Essentially what's happening is I have 5 times a cosine of 5x and then like kind of times a dx or all of that stuff with like in front of a dx. So it doesn't matter if your 5 isn't right in front of the dx. Like another way I could write this would be the integral of cosine of 5x times 5 dx. It's exactly the same thing. So I do have a 5 dx. So I can replace this 5 and this dx with just what that's equal to, which is a du here. And now I have trig still. Trig is okay. I don't have an inside function, so I don't have trig and chain rule in this part now that we've rewritten this. So now we got to think about what the derivative of cosine is, or the antiderivative of cosine. So again, I like to make my little chart: sine, cosine, negative cosine, positive sine. If I'm taking a derivative, I'm going down that ladder. If I'm taking an antiderivative, I'm going up that ladder. So I'm taking the antiderivative of cosine. What do I get? Let's go to Ethan Lee. What do I get here?
Sine
So sine of what?
u. Sine u.
Sine of u, and then what else?
Isn't that it?
What are we missing?
Oh,
Plus
plus C. Plus C. Plus
Plus
C.
C! Plus C! Don't forget your plus C's. All of you on headphones, I'm going to break your ears. Sine of u plus C. So make sure you have that plus C there. Okay. And now this is not our final answer. Our original answer had X's in it. So we need to make sure we have X's in our final answer. All we're going to do, this u was equal to 5x. So we go back and we replace that. So we get sine of 5x plus C. Again, you can always check this by taking the derivative of it. If I took the derivative of sine 5x plus C, I would get cosine of 5x times 5, and then the C would go away, which is exactly what we started with, 5 cosine of 5x. Questions here so far? How are we feeling on this? Thumbs up, good, no problem so far. Thumbs down, really, really confused, somewhere in the middle. Mostly thumbs up. Okay, that's good. That's very good. Awesome. Okay, we'll keep going. All right, here's a slightly more challenging one. So we have x squared times the square root of x cubed plus 1 with the antiderivative and then the dx in there. So x squared times the square root of x cubed plus 1. Okay, Nathan Wise, what do you think we should choose as our u here?
X cubed plus 1.
Totally correct. Absolutely right. X cubed plus 1. And again, the reason we need u sub, I have product rule and I have chain rule in this problem. So that's going to be why I need to use u substitution when I'm taking an antiderivative. Okay, Nathan, what do you get for the next line?
And then the du should be x squared dx.
Hold on. What's the derivative of x cubed?
3x squared.
3x squared. So I should have a 3x squared dx. So you'll notice I don't exactly have that in my problem here. Now, Nathan was noticing, well, I have an x squared dx left, so that's probably what our du is going to be equal to. In this case, it's not. It's close, though. Okay, I don't have a 3x squared dx. So what I actually need to do is I need to divide both sides of this by 3. This is a really important step. Make sure you write this down. They show this in a bunch of different ways on Khan Academy and on, YouTube and all that kind of stuff. Make sure you show it like this. I prefer to write this as 1/3 du. Like I just like to make a new line once I've done this. 1/3 du is equal to x squared dx. Anytime your du isn't exactly the same as what you're left with in the problem, you are allowed to divide over a constant. So I would not ever be allowed to divide over like an x squared or something like that. But if all I have that's different from my derivative available in the problem is a number like 3, right? Because what Nathan saw was I have an x squared dx. I just don't have a 3x squared dx. If all that's in the way is a number, you can always divide that over to the other side. Okay, let's look and see how this now simplifies our U substitution. So our u, that was the x cubed plus 1. All of that's going to be in the square root. I'm going to write that as just raised to the power of 1/2 because I know it's going to be easier to deal with it that way. So that x cubed plus 1, we just replace that with a u. Now, the x squared dx that I had left gets replaced with not just a du in this case. It gets replaced with a 1/3 du. I like to put constants in the front. So I like to put that 1/3 in front of the u to the 1/2. It's totally fine if you put it right next to the du. Okay, it just might make it easier to solve if you put it all the way out in front. Okay, are there any questions on this setup so far? Often when we have to divide something over, this is where guys get a little confused. Again, we're trying to leave x squared dx in the problem, but I didn't have that exactly. I had a 3x squared dx, so I divided over that and got a 1/3. Okay, and now we're not done. Make sure you actually take the antiderivative of this. So the antiderivative of this, well, the 1/3 is just going to come along for the ride. That u is going to get raised to the 1/2 plus 1, so plus 2 over 2. So that means it's going to get raised to the 3/2 over 3/2. Now remember, when you're dividing by a fraction, you're really multiplying by the reciprocal. So you shouldn't have a fraction over another fraction here. You should have it over 3, and then the 2 comes up. So instead of making another fraction bar, just bring that 2 up to the top. Okay, and then I still need a plus c here. Got lots of ways to simplify this final answer. So I've got a 2 as a constant out in front. I'm dividing by 3 and I'm multiplying by 1/3. So that gives me the constant out in front now. Oh my goodness. Come on, spinner. Do I have a volunteer while my spinner acts up? Someone know what we have left here?
Yeah, we'd have a 1/3. And then I'd be a u to the.
Hold on,
Oh, no, sorry.
hold on, Gus.
Plug it in, right? So it'd be a.
No, so I have a 2, a 1/3, and a divide by 3. What constant do I now have out in front?
Isn't it? Oh, 2/9.
2/9. There we go. And then you said plug that in. So what are we going to plug back in?
X plus, or x to the 3rd plus 1.
Good. And then still raised to the 3/2. And finally?
And then plus c. Plus c.
Wonderful, wonderful job. Excellent work. And again, you can check this answer by taking the derivative. If you're not sure, you could always take the derivative to check. When you take the derivative, you're going to need to use something like chain rule probably, because that's the whole reason we used U-sub. So don't forget your chain rule there. Okay, any questions on this problem? Okay, this one's a bit trickier. Sine squared 3x times cosine of 3x dx. This one is a bit trickier. So write this down. Don't get started yet. Just write it down. I'm going to talk through a common mistake I see on this problem. Okay, so we have sine squared of 3x times cosine of 3x dx. What I see some guys do, they're like, well, the inside function on that last one, when we had like a cosine of 5x, it was just the stuff inside of the cosine. So like they on this one might choose a u equals 3x. They get like a du equals 3dx. They don't have that, so they divide it over. And what they end up having is they have like a 1/3. They've replaced all the x's, but they still have sine squared of a u, and then at times a cosine of a u du. So the problem here is even though we did some u sub, we still would have product rule, and I still would have chain rule in this problem. So we haven't picked the right u, okay? We chose a u and we were able to substitute out all our x's, but if I'm still left with a problem where I would have chain rule or product rule, that was not the right substitution there. So that can't be it. Another thing to think about is what sine squared really means. Sine squared is the same as parentheses sine of 3x, all of that thing being squared, then times cosine of 3x dx. It is important to recognize that that's really what sine squared is. Okay, let's see. Let's go to Neil. Neil, do you think you know what u we would choose for this one?
Would it just be sine of 3x?
You are absolutely correct. And I saw some head nods in our class. Great job. Okay, so Neil, then what do I have as my next line of work if we choose u equals sine of 3x?
It'd be du equals cosine of 3x times 3 times
And then-
dx.
Correct. Perfect. Okay, so I have almost all of that exact stuff, Neil. So I've got the sine of 3x, and I've got a cosine and a dx on this side, but I don't have it being multiplied by 3. So what do I have to do with that 3 there, Neil?
Just divide it over. So it'd be
Just
1/3.
divide it over. Sorry, go ahead. 1/3.
1/3 du equals cosine of 3x times dx.
Fantastic job. Excellent work, Neil. Okay, let's go to JJ. JJ, what would I now substitute in to my antiderivative? So what would this look like now? So I'm now going to replace this with all that information that Neil just worked us through. So what would I have?
So I'd sub in the 1/3 du for the cosine 3x times dx.
Perfect. So this gets substituted in for a 1/3 and a du. I'm going to put my 1/3 in the front, my du at the end.
Then you
What
have
else?
a u squared for the
Perfect. Exactly right. So I have a 1/3 u squared du. One thing that you guys are going to see sometimes that makes this even a little bit easier is they'll take that 1/3, that constant, and they'll move it even all the way out in front of the integral sign. So you'll see something that looks like this. That's allowed also, as long as it's just a constant. A constant can go all the way out in front. What that really tells us is the only thing I have to take the integral of is the u squared, and then just multiply it by the 1/3 at the end. Okay, so you're still going to have a 1/3 times whatever the integral is. If you want to put your constants all the way out in front, you can. Okay, JJ, what would the antiderivative of u squared be?
That would be u cubed all over 3. Plus c, of course.
There we go. Plus c, of course. Thank you. Okay, go ahead and finish this out for us, JJ. What would you simplify this down to?
Wouldn't you just leave it as u cubed all over 9 plus c?
So u cubed over 9 plus c is correct, but it's not our final answer because our original stuff had x's in it. So my final answer should have some x's in it.
Okay, so sine of 3x cubed all over 9 plus c.
Perfect. Exactly right. And you might write that as sine cubed of 3x, just like how they started, but the way that this is written is totally fine as long as you know those are equivalent. Okay, excellent, excellent job. This is a trickier one because like I said in the beginning, you could choose a U, but you might end up with something where you still need product rule or chain rule, and then that means you haven't chosen the correct U. Are there any questions on any of this so far? Please ask because it gets a little bit trickier in just a second. Any questions? No? Still feeling okay? Decent, most of you? Yes? Excellent. Okay. Let's go on to this one. This is where your brains might explode a little bit. Not too much, don't worry. So we have the integral of 5x squared over x cubed plus 2 dx. I'd like you to try to set this up. So I'd like you to try to choose your u, take your next line of work, du equals, replace stuff in your antiderivative. See where you get from there. So I'm going to give you about a minute. Everyone should be writing something down. So you're actually trying to figure this one out. If you're nearby somebody in my class, you can chat with them, see what they got, see what they chose. If you get stuck, that's okay. I told you this one was going to be a bit trickier. Let's go to Brian. Brian, what'd you choose for your U?
I chose x cubed plus 2.
Fantastic. That's the correct U to choose. What'd you get for your next line?
Du equals 3x squared dx.
Okay. Do I have a 3x squared dx?
No.
No. So what should I do with that 3?
I multiplied it by 5/3 both sides.
Yeah, so you can do that. I'm going to just say let's divide by 3, but you're right. And that way works totally great. So if you like it that way, that works. Okay. Now what Brian's noticing is we have a 5x squared in there, right? And so he's trying to not only divide by that 3 to get rid of that, he's trying to also multiply by that 5, which is fine. The other thing you can do is just move this 5 all the way out in front. It's a constant. And then multiply it by the 1/3 later. If you want to do it that way, you can. Either way, that works. Oops, that was my timer. Okay, so our next line here is now going to be that we're going to have a 5/3 constant. So this 5 and this 1/3. Or if you did it like Brian did, multiply both sides in that by 5/3, that gets replaced. Okay, so 5/3 du is equal to the x squared dx portion. Okay, so that whole thing is now taken care of. The whole numerator is taken care of. What do I have left, Brian?
We have u to the negative first power.
Yeah, so we have like 1 over u, or the same as what I'm assuming most of you wrote, u to the negative first power. And this is why this problem is tricky. Because when you try to take the antiderivative of this, Brian, what do you then, what happens next?
You get a 0 in the denominator.
Yeah, you get u to the 0 over 0, right? And anything divided by 0 is not going to work. And it's not a does not exist answer. This does have an antiderivative. So it's not does not exist or undefined or anything like that. Power rule actually fails us here. But remember, power rule is not our only rule. Like we had a trig one before. We didn't just add 1 to that and take a derivative, or add 1 and divide by that value. Power rule does not work here. What we have to recognize is what form this actually takes, 1 over u du. Does anyone have a guess at all of what the antiderivative could be? Like, what do I take the derivative of and get 1 over x? Like the derivative of something
ln of
gives
u.
me 1 over x. Yes, ln. So if you guys remember our ln's, oh my God, they're like, no, we have to do ln's and U-sub. Yep, it comes up quite a bit. So this is where we're going to have an ln. If you guys remember, if I were to take the derivative of ln of x, what we would end up with is 1 over x times whatever the derivative of that is, which in this case would be like 1. So if I have a 1 over u, that means our antiderivative is ln. Okay, now it's actually really important how you write this answer. So please make sure you look up here now. This is the biggest reason. Even when guys know that it's ln, they still miss points. We should be writing ln of absolute value of u plus c. So the reason we have an absolute value is because we know ln only works when you have a positive value in there. Like I can't take ln of -1. Okay, now our final answer is not this. Our final answer, we got to plug in our u back in. So we get ln of absolute value of x cubed plus 2 plus c. X cubed plus 2 is not always positive. So in order to have a real answer, I need my ln to be absolute value. Anytime you take an antiderivative of 1 over u, or a hint is if you end up getting something undefined, like if you try to take it using power rule and you get u to the 0 over 0, that's the hint, it's ln, okay? Then you're gonna need ln of absolute value. Go ahead, yes?
You still have to multiply by 5/3.
Yes, you're right, we absolutely do, thank you. I got so caught up in the ln. You are absolutely right. So we had this 5/3 out in front, that 5/3 gets multiplied here. That 5/3 also gets multiplied here. Thank you very much for correcting me on that. Absolutely correct. Other questions? Don't forget your absolute value. Don't forget your absolute value. Don't forget your absolute value. Must be in there. It's not a parentheses, straight lines. Okay, now we're going to talk about U-sub with bounds. U-sub with bounds is a little bit tricky in some ways, but it's actually usually an easier process than all the going back and forth stuff. Okay, so the U-sub part's going to be the same, like just like when we did bounds on Friday. Whenever I had a bounded integral or an antiderivative with like numbers on the top and the bottom of that integral sign, you're just going to start by taking the normal antiderivative just like you normally do. Okay, but this one we have U-sub involved. Make sure you take good notes here. This would be one, if you have a highlighter or a colorful pencil or something, this is a page to mark, because a lot of guys will end up getting U-sub and then they'll totally forget how to do U-sub with bounds. And this is a big question on the AP exam. This is a really, really important topic. Okay, so we're looking at x times x squared plus 1. The whole thing is being cubed. We first need to recognize I would need product rule and chain rule. That means for an antiderivative, I'm going to use U-substitution. Okay, the U I'm going to choose, and don't go too far ahead of me on this one. Some of you feel very confident and I'm very happy for you, but I don't want you to mess this up. The U I would choose, let's go to Ben. What would I choose for my U here?
X squared plus 1.
You're exactly right. X squared plus 1 would be my U. What would my DU be equal to, Ben?
2x.
2x what?
Dx.
Perfect. Remember, we're writing it in our differential form. Okay, now I don't have a 2x dx, Ben, so what am I going to do with that 2?
Divide the 2.
Perfect. So I have 1/2 du equals x dx. Are we comfortable with this part so far? Thumbs up, thumbs down, thumbs in the middle somewhere. Give me a thumb. Good. Okay. All right. Again, don't go too far ahead of me. I want to make sure we set this up correctly, everyone. So from here, we're going to substitute in. I think most of you are comfortable with that portion. We substitute in the x dx, which is this portion, with a 1/2. I'm going to put my 1/2 out in front, du. We substitute in the x squared plus 1, which is right here, with what that's equal to, which is a u. So we end up getting a u cubed. Now, here is the really important part when it comes to the bounds. So before you take an antiderivative, before you do anything else, we also need to deal with the bounds. Here's why. This first one, it's not labeled as such, but what it says is we're really finding an area under a curve, right? If you guys remember, that's what this finds. So we're finding the area under this random curve, x times x squared plus 1 cubed, from x equals 0 to x equals 1. Since this is a dx, everything in the problem is with respect to x, meaning the bounds are with respect to x. So even though it's not labeled as such, those bounds are x bounds. Those are an x equals 0 bound and an x equals 1 bound. When I do U substitution, and I now change this so everything's with respect to U, I also need to change my bounds. I need to make sure I have bounds that are U equals bounds, not X equals. So I need a U equal bound here and a U equal bound here. What we're going to do to figure out what those bounds are is we're going to use the relationship we already set up. U is equal to X squared plus 1. Anytime in this new integral, that's what U is equal to. U is equal to X squared plus 1. So for example, when I have X equals 0, and I want to figure out what the corresponding U is, all I do is plug 0 in for that X. I get 0 squared plus 1, which is equal to 1. For the top bound, when I want to evaluate what is U equal to when X is equal to 1, again, I use that relationship. 1 squared plus 1, I get 2, and that's my top bound, which is 2 now. You don't need to write the U equals. I'm just writing that so you guys can see how this works. Really, it's just now our new bounds are 1 and 2. On the AP test, there are several questions where they don't even ask you to solve an integral. They just want to see, can you set this up? And the biggest trick that guys miss is that they forget how to change their bounds on that. Okay, so now let's go through this. Now there's a reason also why U sub with bounds is even better, and I'll show you in a second. Okay, are there any questions on changing our bounds so far? Okay, so now I'm going to take the antiderivative. I'm going to take that 1/2 along for the ride. I'm going to get U to the 4th over 4 plus C. Now, since it's bounded, you guys remember the C is going to cancel out. So it's actually okay if you forget the C when it has numbers on your integral. If you forget the C there, it's actually okay because the C is going to cancel out every time. I just like to write it so we get in the habit, we don't forget. And now we're evaluating this from 1 to 2. Here's what's really nice about U sub with bounds. I do not need to go back to this stuff at all again. So in all the previous problems, I had to go back and substitute X back in. I had to go back and do all that stuff. We've already changed our whole thing, including our bounds, to be U's. So I never need to look at this stuff again. I'm going to be done once I actually plug in this and this in for my U. I do not need to go back to X squared plus 1. Okay, which makes the work easier. It makes it quicker. Make sure you're following that. So my constant out in front would be 1/8. I'm going to have a U to the 4th, which is 2 to the 4th plus C, minus a 1 to the 4th plus C. Again, I just took these constants all the way out in front as a 1/8. And now I'm simplifying this. I'm not going back to X squared plus 1. I'm not going back to 0 and 1. I changed my bounds. All I have to do is plug those in. The C's cancel out. I still have a 1/8 out in front. 2 to the 4th is 16 minus 2 to the 1st. I'm sorry, 1 to the 4th, blah. 1 to the 4th is 1. So I end up with 15 over 8 as a final answer. Any questions on this problem? You must change your bounds when you're doing U substitution and there are bounds. Some guys try to skip that step and try to go back to the X's. That's incorrect and you're going to miss points. Okay, and you're going to do more work and you're going to get lost. Blah, da, 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 da. Let's do another example with bounds. This one is harder. We only have 5 minutes. Wahoo Toshner. Looks like there's two U's to choose from. Like what most guys are going to choose is sine X. Here's the issue. U is not our sine X. Okay, but look up here and I'll show you why. So if you try to choose U equals sine X, you get du equals cosine X dx. Not 1 over cosine X dx. Like, yeah, cosine X and dx are both in here. But really what that integral is sine of X times 1 over cosine X dx. So I can't choose cosine X dx. I can't get rid of it because I don't have cosine X times dx. So there's basically only one other option to choose. We're going to choose U equals cosine X. We get du equals negative sine X dx. We don't have a negative there, so I'm going to put that negative over to the other side. Negative du equals sine X dx. and I'm going to start substituting things in. Sine x dx, that's just equal to negative du. I'm going to throw a negative all the way out in front where I like to put my constants, and my du is going to go at the end. That has replaced this portion. Sine x dx got replaced with a negative du. Now what I have left in here is I still have 1 over cosine. Well, cosine is just equal to u, so that goes here. We get 1 over u du. Now I have to change my bounds. So again, this is where trig comes in. We got to know our unit circle. I just went over unit circle with my pre-calc guys, so there's a video on my channel if that's helpful. Go ahead and watch that. We need to figure out what cosine of 0 is for our bottom bound. Again, we're using the relationship u equals cosine x to figure out what my u bound is that's going to go right here. Right, so all I do is plug that x in. I'm going to get cosine of 0 equals 1. That's going to go down here as my bottom bound. So u equals 1 there. To figure out the top bound, I plug in pi over 3 in for cosine. That's this taller angle here, pi over 3. That has a smaller x value. We get a value of 1/2. You'll notice in this problem, my bottom bound is actually bigger than my top bound. That's okay. That's going to happen sometimes. If you want them to be in the right order, what you can do is you can actually flip them if you multiply your whole integral by -1. So what I'm saying is this is actually totally equal to the integral. Well, if I multiply by -1, that negative is going to go away, of 1/2 to 1. If I ever want to flip my integral so that my bounds are in an order I prefer, all I have to do is multiply it by -1. So that made it a little easier. I'll be able to plug in the top number first, or the larger number as my top bound. And I was able to flip over my integral and make it negative. Okay, so we've replaced all our bounds. We don't have to go back to this x ever again. We're done with him. We're only going to use our new stuff. I have the integral of 1 over u du. Justice, what's the integral of 1 over u?
We're gonna have a negative, so negative ln of absolute value u.
Okay, so you're on the top one. Is that which one you're doing?
Yeah.
So I switched to the bottom one just to get rid of that negative and make it easier. So that negative went away because we flipped our bounds, if you remember. So what do I get here? You're right though. Ln of?
Ln of absolute value bars u.
Correct. Don't forget your absolute value bar. And again, since it's bounded, you don't really need your plus c. Like if you forget your plus c here, that's okay. We're going to evaluate this from 1/2 to 1, meaning I'm going to plug in my 1 first, ln of 1 plus c minus ln of 1/2 plus c. Now at this point, you don't really need the absolute value bars because 1 is positive and 1/2 is positive, but it's not wrong to include. So if you're worried about missing it, just include them every time. Okay, we can simplify this quite a bit. Our c's cancel out. Does anyone know what ln of 1 is? We've only got less than a minute. ln of 1, what's that equal to? E to what power
0
equals 1? There we go. So we get 0 minus ln of 1/2. So final answer, negative ln of 1/2. You would have gotten this answer, by the way, if you didn't flip over your bounds. If you left it this way, you would have gotten that same answer, which is fine. Okay, it's 8:50 now. That's it. I recorded this. I'll throw this up on YouTube later today if you need some additional help. Otherwise, get going on your homework, and I will see you guys tomorrow. Have a wonderful day.
Thank you.
Thank you.
Stay on if you have questions, y'all. Thank you.